Hello everyone, welcome to ISCC 2023 tutorials. My title is All Digital Plls from Fundamental Concept to Future Trends. For a brief self-introduction, I received a master's degree in electronics engineering from Waseda University in 2004. I then joined the Toshiba R&D Center since 2004 and now within a wider R&D group as project leader. My interests are in high-performance mixed signal circuit, such as digital analog phase loops, low-power transceivers, and automobile radar SoCs. This is the motivation of these tutorials. Recently, phase-locked loops PLL has become more and more indispensable. Almost all components for cyber-physical IoT systems, a GPU, CPU in a data center, and a wireline or wireless communication, need PLL for system clocking and data recovery, RF mixing. First of all, grasp basic of frequency synthesis, including PLL, and then analyze the principle and benefit of digital PLL with technical evolution trend, and finally try to analyze and predict the future evolution trend. This is the outline of my tutorial. First, I will explain about the background of frequency synthesis. And next, we need to study the basic of all the digital PLL, including the fraction and operation and splice stones. And next, advanced digital PLL. And finally, we discuss about the future trend prediction and finally summarize my talk. The first, background of frequency synthesis. In this slide, I would like to discuss the quality required for frequency synthesis for each application. Frequency synthesis is used in many places, such as mixer in wireless communication and sampling in data converter. Each application requires different characteristics. For example, with wireless, it is necessary to precisely match the frequency of the local signal to the desired channel. Phase noise in the frequency domain degrades signal quality, so it's much important. Similarly, in the sampling of the data converter, it is necessary to synchronize the clock timing with the digital signal processing that follows. In this case, fluctuation on the time domain causes error, degrading the signal quality. Hence, it's much important. These are basically the same noise and jitter and noise frequency noise, with the only difference being whether to look at the noise in terms of frequency or time. This section explains the relationship between the periodic jitter and the frequency noise. Periodic jitter is a time fluctuation that occurs in one clock cycle. And the frequency noise is a frequency fluctuation that occurs in one cycle. There is such relationship, and it can be easily converted to each other. Next slide explains the relationship between the phase jitter and phase noise. These can be regarded as long-term or integrated form of the period jitter or frequency noise. rather than one cycle. The longer the integration time, that is the longer the observation, and the greater the jitter. In frequency domain, that translates to integrating down to low offset frequency. Phase jitter and phase noise have such a relationship and can be easily converted. Next, we discuss how to generate high quality clocks with low jitter and phase noise. The simplest clock generation method is to use a free running VCO. There are two types of VCO. The harmonic type, which mainly uses positive feedback for oscillation, and the other is a relaxation type, which uses periodically switch on and off of such as charge pump. The oscillation frequency is controlled by a voltage input. The applied input voltage determines the instantaneous oscillation frequency. Consequently, a VCO can be used for frequency modulation or phase modulation by applying a modulating signal to the control input. There are two main types of the harmonic type VCO, LC tank and ring. These have clear performance design trade-offs. LC has low phase noise because the resistance value that causes positive feedback loss is very low. The area is large because it requires spiral inductor with metal wiring. On the other hand, the area for ring VCO is small because it can be realized only with transistors such as inverters. However, the phase noise is poor due to large loss of positive feedback. For example, if clock PLL with a jitter of lower than 1 picosec is designed with LCVCO, it will require large chip area as shown here. So, we need to consider the design with a good understanding of PLL performance factor is very important. So I explained the simplest clock generator is a VCO, but the phase noise and the phase jitter diverge significantly over time. The longer the integration time, that is, the longer the observation, the greater the jitter. If the jitter observation time is Tm, the lower limit of the phase noise integration and phase noise observation interval is 1 over Tm. In other words, the longer the observation time is, the lower the offset frequency will be integrated. And the jitter, which is the expression of this energy integration, will also diverge. So, free running VCO is a very low quality clock. Frequency accuracy of free running VCO is also a problem. In order to accurately down convert wireless communication, it's necessary to match the local frequency with a desired channel at a very high accurate level. Free running VCO have large frequency fluctuation due to the transistor process fluctuation or variation and I think metal wiring parasitic variation. So how can we generate high quality clock with low noise and no frequency fluctuations. First of all, simply thinking about the voltage, the simplest method is to use feedback. In other words, prepare a clean standard reference that does not fluctuate and follow that the output as much as possible through feedback. By increasing the feed-forward gain, the input and output relationship is determined only the feedback coefficient. In the case of the operational amplifier. In other words, if high gain and low noise feed-forward gain can be achieved, it is possible to generate an accurate and low noise output voltage determined by the feedback factor. So can we do the same in the phase domain? The answer is yes. That's a PLL. Phase domain feedback can be used to generate an accurate output clock determined by the feedback factor. Here, accurate means low phase noise and high frequency accuracy. Prepare a very clean reference clock source with low phase noise and a very high feed-forward gain. By following the output as much as possible, it's possible to generate a high-quality clock with low noise and no frequency fluctuation. However, this is only possible if a high gain and low noise feed-forward gain can be realized in the phase domain, not voltage domain. When realized in the phase domain, the feedback factor becomes the frequency division ratio. And by changing this, a clock with any frequency can be obtained. The output quality of the PLL is mainly determined by the feed-forward gain and the quality of the VCO. The main topic of this lecture is unravel the flow of technological evolution, such as how various means with the analog or digital circuit have been used to realize these feed-forward gain with small area and low power consumption. First, let's look at the feed-forward gain of the most basic PLL called Type 1. A Type 1 PLL consists of a phase comparator and low-pass filter and VCO and frequency divider. The voltage function of each block is expressed as here. Phase comparator converts input and output phase difference to voltage with the gain of KPD. A low-pass filter smooths the voltage with the transfer function of the LFS. The VCO converts the voltage into frequency with the gain of KVCO, then integrated it over time here and convert it to the phase. So in other words, the total transfer function is KVCO per S. The multiplied feed-forward gain is expressed as this, resulting in a simple first-order integrator. Next, the Type 1 PLL loop bandwidth and signal transfer function and noise transfer function will be explained. PLL loop bandwidth is determined by the unity gain frequency of the feed-forward gain. Signal transfer function STF is a transfer function from the input to the output phase of PLL and is expressed like this. And noise transfer function NTF is a transfer function from the VCO phase change, including noise, to the output phase, and is expressed like this. These have the LPF and low pass filter and high pass filter characteristics respectively, with the PLL loop bandwidth as their cutoff frequency. That is, type 1 PLL can suppress VCO phase noise by a first-order high-pass filter. Next, let's look at the forward gain of the PLL called type 2. And the big difference from type 1 is the presence of the charge pump. The phase comparator detects not only phase difference, but also lead and lag of the frequency. The phase error can be integrated into the capacitance of the charge pump. The feed-forward gain has two origin poles due to the VCO and the charge pump. It's classified into type 1 and type 2 according to the number of the origin poles. If type 2 is closed loop as it is, it will oscillate without phase margin. So stability is maintained by inserting the 0 point implemented by the resistor in the loop filter. Next, the STF and the NTF of the type 2 PLL will be explained. STF has the same characteristics as type 1, but NTF becomes the second order high-pass filter because the order of the integrator increases to two level, from 1 to 2 origin pole. This makes it possible to further suppress the phase noise of the VCO at a frequency lower than the loop bandwidth compared to the type 1 PLL. So far, we have explained the relationship between the loop bandwidth and the NTF and STF. The higher the loop bandwidth and the higher the order of the PLL, the more the VCO phase noise can be suppressed. On the other hand, the lower the loop bandwidth, the higher the phase noise of the VCO and the lower the phase noise of the input signal. In other words, the higher the loop bandwidth, the more the PLL will follow to the input phase, such as from crystal oscillator. And on the other hand, the lower it is, the PLL more follows to the VCO phase. So, if we use poor phase noise ring VCO, the broadband type 2 PLL is more advantageous. On the other hand, if the LC VCO is used, lowering the bandwidth will reduce the total phase noise, and lowering the order of the PLL will reduce the design cost. It becomes a more simple design compared to the type 2 PLL. Please note that it is important to design for optimum loop bandwidth according to the type of the VCO to be applied. I would like to explain the PLL performance metrics here, mainly used in these tutorials. Earlier, I explained the relationship between the phase jitter and the phase noise. Here is a jitter FOM. This is an index that shows how much phase noise or phase jitter was suppressed by dividing the feed-forward gain of the PLL or the VCO architecture. The smaller the power and jitter, this FOM becomes less. It means better PLL performance. Uh, and furthermore, in these tutorials, we will explain the performance trend and the evolution process of the PLL using the disk graph, plotting the GTFOM as a horizontal axis uh, as a chip area. To the lower left is a superior PLL that achieves low jitter with less power and chip area. PLL using type 1 and type 2 ring VCO and LC tank VCO explained so far is plotted around here. There is a clear trade-off trend between the jitter and area using ring and LC. Here, we will explain the PLL loop bandwidth design required for not performance, but also for each application requirement. In applications such as clock and data recovery, the input data is used as a reference signal of the PLL. So the PLL is required to have phase filter function to remove the noise of the input data. In this case, it is better to adapt the low noise oscillator as a VCO, such as LC VCO, and lower the loop bandwidth so that the phase much more follows to the clean VCO. On the other hand, applications such as dynamic voltage and frequency scaling requires low jitter, as well as fast lockup fast frequency change when dynamically changing the frequency. The lockup response is proportional to the loop bandwidth. Therefore, as shown here, type 1 is more suitable for DVFS application than type 2 because it is easier to enjoy the stability and more wide loop bandwidth is easy to realize. The main characteristics of the feedback amplifier are noise, the power, and area, and the voltage step, and responsivity. These clearly have design trade-off, and the design key factor are feed-forward gain, and gain bandwidth, and feedback factor. Similarly, key characteristics of PLLs with feedback in the phase domain, including phase noise, jitter, and area, power, and frequency step, and frequency accuracy, and lockup time. These clearly have design trade-off, and the design key factor in the phase domain is a feed-forward gain and loop gain or loop bandwidth, and the type 1 or type 2 period types and visual types. Uh, I think very similar to the feedback amplifier design. Here is the performance trend of PLL up to last year, which will be explained from now on. A big shift has occurred due to the innovation of all digital PLL from analog PLL. Since then, digital PLL has evolved into the advanced digital PLL with the introduction of technologies such as DTC or divider-based or DLL and high performance TDP. While unraveling those flows, we will explain the principle of operation as simply as possible. Next section, we will focus on basic or digital PLL. First of all, we need to know what is fractional N operation and fractional sparse. First, we will explain the difference in operation and design when the division ratio of the PLL is an integer. This figure shows a case where the output phase is locked with a division ratio of 4 with respect to the reference phase in an analog type 2 PLL. After the time T-ref has elapsed, the phase of the reference signal and the output of the friction divider advanced by 2 pi, while being synchronized by the negative feedback of the PLL. The output phase of the VCO advanced 2 pi multiplied 4, so 8 pi during this time. This figure shows the case where the analog type 2 PLL logs the output phase with respect to the reference phase with a division ratio of the 4.5. The division ratio is switched between the 4 and 5 by the delta sigma modulator. During the period when the division ratio is 4, the output of the frequency divider is slightly ahead of the reference phase. Conversely, during the period when the division ratio is 5, the output of the frequency divider is slightly behind the reference phase. On the average, a division ratio of 4.5 will lock the visual to the reference phase. However, when observed in the short period of time, a phase shift naturally occurs. This phase shift becomes a fractional spur, and in order to spread it in terms of frequency, the frequency division ratio 4 and 5 are randomly switched by delta sigma modulation. So here is a final consideration in the tutorial of the peer loop bandwidth design. So the key design factor is fractional sparse. The fractional spur is a major trigger for the digitization of PLL. The transfer function from the fractional spur to the output phase is the same as STF. In other words, the narrower the loop bandwidth, and the more the low noise fractional PLL can be achieved. But naturally, the chip area of the analog filter and the phase noise of the VCO becomes the issue. If we need to alternate the fractional spur uh, of the 100 kilohertz 20 dB. We need around 10 kilohertz cutoff analog loop filter is required. Next, fundamental and digital implementation of ADPL is shown. Uh, I think all digital PL is a very, very big innovation. All digital PL can completely eliminate the loop filter chip area problem for the fractional spur. A loop filter can be replaced with a small digital loop filter. As you know, ADPL can get the other great benefit from CMOS scalability. The power consumption of the digital block will shrink with process scaling. The low development cost is also very attractive. You can reuse, for example, you can use the HDL for one application to another one design, which reduces the design and development cost. Moreover, the phase digitization by the count and TDC in the ADPL make it easier to use the calibration for enhance the PPT robustness. For example, the gain of the DCO, digitally controlled oscillator. Since the loop filter fluctuation function as a charge pump and 0 point, here the basic operation of the TDC is explained. The TDC measures the fractional delay difference between the reference clock and the next rising edge of the digital clock, as shown in this figure. Its resolution is a single inverter delay, T delay, which in deep submicron CMOS process is considered the most stable logic level regenerative delay and is shorter than 20 picosec. Phase error phi e can be calculated by subtracting the fractional delay difference delta TR from the DCO output phase 2 pi. However, the problem here is the variation of the T delay. As T delay increases, the actual TV digital value decreases accordingly, and conversely, as T delay decreases, the actual TV digital value increases accordingly. If one period of the DCO is set to a fixed value, that is estimated first once, the code value representing 2 pi of the full scale will vary greatly, so resulting in a large full scale error as shown here. It will cause severe fractional spur and jitter. Therefore, in practice, full-scale error is prevented by always detecting how many T delay one cycle of the DCO corresponding to, and calculating the phase error phi e using the actual TV digital value. Actually, TB is calculated from the difference of delta TF and delta TR. Those are the fractional delays between the reference clock and reference clock and the next DCO rising edge and falling edges, respectively. This slide describes the ADPL digital loop filter. A digital loop filter consists of an integrator and a 0 point, just like analog one. A digital integrator with a coefficient low plays the role of the integrator, composed of a charge pump and a capacitor in the analog PLL. A parallel path with a coefficient alpha serves as a 0 point, with a resistor connected in series with the capacitance in the analog PLL. The IR filter removes high-frequency ripple. In addition to the merit of the digital implementation, there is a great merit of being able to switch between type 1 and type 2 in terms of software. So here is order PLL's Z to S domain model. The transfer function of the order digital PLL in S domain model is the same as the type 2 analog PLL. So its STF and the NTF and the open loop transfer function is same as analog PLL. However, all digital PLL can easily narrow the loop bandwidth with the area efficient digital loop filter, so easily suppress the fractional spurs more than the type 2 analog PLL. However, this all benefit is built on the assumption that the time resolution of TDC is sufficiently high. The TDC performance, especially quantization noise and nonlinearity, critically dominates that of ADPLL. This figure shows the phase behavior of DCO output when the TDC is ideal, blue line, and with quantization noise, red line, and with the nonlinearity, and another red line. Assuming that the fractional frequency is much lower than the loop bandwidth of the ADPLL, when the ADPLL is locked, the DCO phase just tracks input phase with just off by the Qn and NL of TDC. Hence, generally they dominate the PLL phase noise and fractional spurs. The key topic of the research of the all digital PLL from 2002 to about 2015 is always about the high performance TDC. The representative approaches for improving the quantization noise are the Barnier delay line here and the time amplifier here. The Barnier delay line utilizes a two delay line having different delay for the DCO input and reference input path. And the time resolution is determined by their difference, resulting in a higher resolution. On the other hand, time amplifier enhances its resolution by amplifying a time residue of the first stage. The amplified information is quantized at the following fine stage as the same manner as the coarse stage using the delay line. However, the power consumption of these techniques are quite high because they need many power-hungry buffers in the high-speed GCO output signal path. And here, performance trends up to 2010 are shown. In the 5 years since 2005, when ADPLL was announced, the performance of the PLL have evolved dramatically. The reason for this is that the chip area and power can be greatly reduced by digitizing the charge pump and loop filter. We introduced the cancellation technology for the fractional path. The next section. From here, I would like to explain the further evolution of the digital PLL. First is the introduction of the divider. And here we show the divider-based digital PLL. This greatly contributes to improving the performance of the TDC. By lowering the clock rate of the DCO output to the same level as the reference signal, the power consumption of the high-resolution TDC, such as time amplifier or barrier delay line, mentioned earlier, can be reduced. Furthermore, the next rate TDC, which will be explained later, enables even higher resolution and low power consumption. However, like the analog PLL, there is a demerit that causes the problem of the fractional spur caused by the switching of the delta signal modulator of the division ratio. However, a great benefit from CMOS scalability, such as chip area and power shrinking, low development costs are still maintained. Next, high-performance TDC and fractional spur cancellation techniques. This slide shows a concept of the time-stored TDC. A time-stored TDC is a type of the TDC that stores time difference and the phase difference information between the reference signal and DCO output as some kind of the physical quantity, and then convert it to the digital. In this example, the phase difference between reference and DCO is converted to the voltage by charge pump, and then converted to the digital data by using ADC. ADC can be chosen for case by case, such as single slope, SAR, pipeline, or cyclic. If no noise, the time resolution of the time-stored TDC is mainly limited by the ADC LSB voltage. So, time-stored TDC is effective approach for improving the quantization noise and the non-linearity of the TDC. TDC shown in this slide is a single-slope time-stored TDC presented at ISSCC 2016. TDC mix the concept of the time-to-voltage conversion and the single-slope AD conversion so that the weakness of them are compensated each other. The TDC shares a current source between the change pump for time-to-voltage conversion and the single-slope generation. Moreover, DCO integer phase counter is reused for the single-slope AD conversion, which results in the DCO full scale is determined by the ratio of the capacitor for the time-to-voltage conversion VF and single-slope generation VRAMP. Consequently, much better INL with low power is achieved without DCO period detection and any calibration. This slide shows a time-stored TDC that uses the first-order noise shape ADC. A ring oscillator is operated for a period corresponding to the phase difference here between the reference signal and the frequency divider output, and the signal is converted into the digital value with the resolution of the one inverter stage of the ring oscillator. The point here is to hold the voltage state at the end of the operation period of the ring oscillator. It can be said that the time information is stored in the parasitic capacitance of the inverter after the gate by the transistor switch. The ring oscillator always starts operating from the state of the previous operation cycle. As a result, the first-order high-pass filter can act on the quantization noise. This is very effective in reducing the quantization noise because it is driven to high frequency by the noise shaping, and after that the PLL ADPLL low pass filter SDF function is can furthermore suppress the quantization noise. In addition, this TDC is also devised to reduce the inverter delay of the ring oscillator by multipass. Each stage input of the gated ring oscillator shown here are connected to the combination of the previous delay stage. By optimizing the number or placement and weight of the connection, each stage begins to the transition well before the full transition of the immediately preceding the stage is completed. The resulting effective delay through the stage is reduced to 6 picosec, from 35 picosec to 6 picosec. Here, the transfer function of noise generated in the frequency divider using delta sigma modulation will be explained. As mentioned before, the fractional spa generated by the switching of the frequency divider is diffused to the high frequency by delta sigma modulation. It can be treated almost as quantization noise, and the transfer function for this quantization noise is the same as STF and has a low-pass filter characteristics. Therefore, as shown here, DCO phase noise dominates when the loop bandwidth is narrow, and the quantization noise dominates when the loop bandwidth is wide. With the advent of high-performance TDCs, expanding the loop bandwidth to some extent, and which contribute to the suppress the DCO phase noise, will lead to further improvement in JIT-FOM. Therefore, a technique for reducing the quantization noise itself of the delta sigma modulation type flexible divider has been desired. This slide displays the divider-based digital PLL with quantization noise cancellation circuit, which is completely digital in its implementation. The goal of this circuit is to remove the quantization noise introduced by the designing action of the divider. Benefit from the down-speeded DCO output, such as easy-to-use time-stored type, and improves the quantization noise and the non-linearity of TDC are still maintained. This slide shows the detail of the quantization noise cancellation circuit. Quantization noise of delta sigma divider is manifested in the GRO output signal, phase error signal UK, as a scaled version of the accumulated quantization noise XK. Just scaled. So proper scaling of the XK must be performed before the subtracting it from the UK, and the scale factor is determined by a correlation circuit composed of the digital multiplier and accumulator and first order IR filter. It's composed of the feedback loop. Due to the high resolution of the GRO-based TDC, the correlation feedback loop can be designed to have a reasonably fast settling time. So this scale factor calibration time does not matter for the ADPL operation. This slide shows the divider-based digital PLL with gated ring oscillator noise shaping TDC and quantization noise cancellation circuit. High resolution digital phase detection is performed with noise shaped GRO TDC. And another original point of this PLA is an additional 4-bit MIM capacitor bank is included in the VCO to improve its tuning range. And using the character and digital to analog converter DAC for the LCDCO control scheme. The quantization noise circuit for divider, quantization noise, and the GRO for TDC realize outstanding jitter performance, 0.2 picosec. However, relatively large power and area are needed Uh, so it's, I think, due to the less process scaling merit of the LCVCO, DAC, and the parameter tuning uh, architecture. So the DCO frequency is controlled by analog reach digital to analog converter. This slide shows a divider-based digital PLL with single slope TDC. Downspeeded TDC input and the counter sharing technique realize much power reduction, as mentioned before. However, TDC maximum resolution depending on the divider ratio limits the PLL jitter performance. So I'd like to explain the performance trend up to 2015. The graph is shown here, and the jitter FOM of this period was improved by introduction of frequency divider and high performance time stored TDC. On the other hand, however, the increase in chip area seems to be due to the ADC used in the time stored TDC, maybe. GADC used for this requires a certain amount of chip area. In addition, the divider-based digital PL has a large difference in jitter FOM with or without QNC. QNC is necessary for divider-based digital PLL. Next, I'd like to introduce a further evolution of digital PLL with the introduction of DTC. DTC controls the divider output phase or reference input phase in response to the frequency control word, so that the fractional phase error approaches to zero. The DTC can be regarded as a frequency divider with high time resolution and can also be regarded as a quantization noise cancellation circuit for frequency divider. The phase difference input to the TDC by the DTC is extremely narrowed from NiPi to the time resolution of the DTC. And high resolution TDC, such as linear delay line and time amplifier, can be used with low power. Benefits of the delta sigma quantization noise cancellation and downspeeded DCO output are still maintained. This section describes the operation of the DTC as a high-resolution frequency divider. Fractional phase division can actually be physically realized by combining a DTC with a regular counter-based divider. As shown here, the phase of the DCO after integer division and fractional division by the DTC is made to track the reference phase by accumulating the FCW. If full-scale delay of DTC does not match full-scale NiPi of the DCO, it causes large glitches, as in the case of the TDC full-scale error. Hence, DTC gain G must be adjusted so that the full scale becomes NiPi. TDC full scale error is manifested in the fine TDC output. As a phase error signal and as a scaled version of the accumulated quantization noise, QK. Proper scaling of G must be performed before multiplying it with DTC, and the scale factor is determined by the correlation circuit, like a comparison of the digital multiplier, accumulator, and first-order IR filter. Due to the high resolution of the fine TDC, the correlation feedback loop can be designed to have a reasonably fast settling time, as in the case of the QNC gain calibration. Here we will explain the performance trend of DTC-based digital PLLs together with digital PLLs introduced so far. This is an example of using a time amplifier-based TDC with low power by introducing the DTC circuit. It achieves a very high jitter FOM. This also uses a time amplifier-based TDC, but by using a single slope DTC, a high resolution of 10 bits is achieved with extremely low power consumption. As a result, an amazing jitter FOM has been achieved, minus 246 dB, and the chip area is also small. This is the performance trends up to 2020. It can be seen that the introduction of the DTC has dramatically improved the jitter FOM and chip area. From here, it may be a little digression, but I would like to mention future digital PLL performance trends. The introduction of DTC made it possible to use fine TDC with low power. The ultimate fine TDC is a 1-bit TDC. So this is a band phase detector. Since it can be implemented with a single flip-flop, it is the ultimate form in terms of the chip area and the power consumption. However, for stable operation of the band phase detector with sufficient gain, it needs input noise to reasonably deserve the output 1 or 0. So sufficient dithering is needed to keep the stable gain of the band phase detector. However, sufficient level noise can be get from the both DCO phase noise and DTC quantization noise in the digital PLL. Here, two papers about DTC-based digital PLLs using band phase detector are introduced. This paper realized the jitter FOM of less than minus 250 dB by using the band phase detector and DTC in the reference clock side, not divider output. DTC resolution is improved by the method explained earlier. In this paper, jitter FOM below Also minus 250 dB is realized by applying noise shaping to the phase noise of the band phase detector. Performance trend up to 2022 are shown. It can be seen that the introduction of the DTC and the band phase detector has improved the jitter FOM to below minus 250 dB. Here, I'd like to talk about the all digital PLL evolution history. A big invention of the all digital PLL in 2005 set the people free from the complex analog design to some extent. However, researchers are not satisfied with the quantization noise of TDC, so they improve it by introducing the divider, and by down the DC output speed and high performance TDC, such as time stored TDC, can be utilized for quantization noise and the nonlinearity of the TDC suppression. In addition, not only solve the problem of the divider quantization noise by QNC, but also with the introduction of the DTC and the band phase detector, researchers have taken digital PLL to the almost extreme level. From the perspective of the evolution of DCO, we would like to keep an eye on the potential of the digital MDLL that can be designed with the all block with the standard cell instead of the LC tank. Digital MDLL can also benefit from the DTC and band phase detector. In the future, technology for reducing the fractional spur and jitter for the delay line, which are currently poor performance, it will become possible through fine process on the order of the several nanometer or less, very, very fine process. We would like to keep an eye on what will happen with further process evolution. So it's very, very interesting. Let's plot both the performance trend of the digital PLL and the digital MDLL using a band phase detector. Although the digital MDLL has an area advantage compared to the band digital, the jitter FOM still falls short of the band digital PLL. However, what will be occurred if the technology and the process evolution mentioned earlier, we have to keep an eye on it. Let me summarize my tutorial. First, frequency synthesis and PLL has more and more indispensable for recent growing demand of IoT system. PLL is a phase domain feedback system. to generate accurate frequency phase output. Major applicative constraints and design challenge are fractional N operation with low jitter, the low phase noise, and low fractional spur. All digital PLL is a major breakthrough in frequency synthesis, greatly mitigates trade-off between loop bandwidth and the chip area penalty of loop filter. Advanced digital PLL with divider and DTC continue to improve jitter FOM by cancelling the delta sigma modulated quantization noise and by making required TDC dynamic range very narrow. Ultimate TDC implementation is a 1-bit Bambam phase detector. While Bambam digital PLL with divider and DTC continues being mainstream, it must be taken into consideration that Bambam digital MDLL benefit much from CMOS process scaling. Here, I would like to introduce paper to this year. Session 4, 4.2. This paper is a good example of the ring ratio-based analog PLL. And 4.3 and 4.5 is a good example of the DTC-based Bambam digital PLL. Session 41, fractional MDLL with excellent DTC nonlinearity cancellation. And 14.2, innovative DTC IN calibration technique using auxiliary PLL. Finally, my message is write PLL in the right place. In some cases, analog PLL using a type 1 and using a ring oscillator may be the optimal solution. Very, very simple design. I think this is a great attraction of the integrated circuit design. We hope that this article will be of help to you in your future circuit design. Thank you so much for your attention.